reads that an impure sample of barium hydroxide of mass 1.6524 grams was allowed to react with 100 cm cube of hydrochloric acid of concentration 0.2 mole per decimeter cube. So we have a reaction that's happening between barium hydroxide and hydrochloric acid, and I'm going to write the equation first for this reaction. It's a reaction of a hydroxide, which is a base, with an acid, and it's going to produce a salt and a water molecule. Ba is in group 2, so it's 2 plus, so the formula is BaOH twice, and barium chloride is also BaCl2. Ba is 2 plus, Cl is minus 1. So this is your complete balanced equation. And let's add the information as well. The mass of this impure barium hydroxide is given. It's given as 1.6524 grams. But remember, this is impure, which means that barium hydroxide mass is not 1.6524 grams. There would be impurities involved in the sample. Plus, the other thing that's given is you're given the volume of HCl, which is given as 100 cm cube, and you're also provided with the concentration of the acid, which is 0.200 mole per decimeter cube. So this information is also provided. And the question then reads, when the excess of the acid was titrated against NaOH. So he's saying that the acid is in excess. So the acid is going to be in excess, which means that there is going to be leftover acid, and that excess acid was titrated against sodium hydroxide. So NaOH, sodium hydroxide, he's reacting the excess acid with sodium hydroxide. So let's add that as well. So the leftover acid in the first reaction, HCl, is now being reacted with NaOH. So here's your leftover HCl, and that's being reacted with NaOH, and it's going to produce NaCl and water molecule, and all the ratios are going to 1:1. It's a balanced equation, and we can read some information about the NaOH that's being used. He's saying that it's 10.9 cm cube of sodium hydroxide solution was required, and you're not given the concentration, so only the volume is provided. So volume of NaOH that's used is 10.9, and let's also check it's exactly 10.9, accurate up to 3 significant figures. So it's 10.9 cm cube that was used. So the concentration of NaOH is missing. But the question then reads further that 25 cm cube of the sodium hydroxide required 28.5 cm cube of the hydrochloric acid in a separate titration. So there's another reaction that's happening in a separate titration, and in that separate titration he's reacting hydrochloric acid with sodium hydroxide again, and 25 cm cube of sodium hydroxide with 28.5 cm cube of hydrochloric acid, and there's a complete neutralization reaction that's happening. So a separate reaction is happening. So let's write that separate reaction now. Over here is your separate titration that's happening. HCl 28.5 cm cube reacting completely with NaOH, whose volume is 25 cm cube, and I don't know the concentration of this NaOH, but the concentration of HCl was given in the question. If you look at the third line, he's saying hydrochloric acid has a concentration of 0.2 mole per decimeter cube. So we have the concentration of HCl, which is 0.200 mole per dm cube, and accurate up to 3 significant figures. So why are we given this extra information that there's a separate titration happening? The reason you're given this information is that using HCl's volume and HCl's concentration, you would be able to find the concentration of this unknown NaOH, because this NaOH would be needed because at the end of the question states calculate the percentage purity of the sample of barium hydroxide. Now the only way you can find the percentage purity of the sample of barium hydroxide is if you know the moles of barium hydroxide, and you can only know the moles of barium hydroxide if you know the moles of HCl, but HCl is in excess, so you need to know what amount of HCl is left over so that you can know what amount of HCl moles reacted with barium hydroxide. So to find the leftover HCl, you would need to find the moles of NaOH, and that can only be done if the concentration of NaOH is known. So this separate titration is going to help you find that. they've given you the volume and concentration of HCl that's reacting. They've given you the volume of NaOH. Using this information, you should be able to find the concentration of NaOH. And the way to do that is that you're going to first find the moles of HCl. So moles of HCl would be N would be concentration multiplied by volume. So it's going to be 0.2 mole per decimeter cube multiplied by 28.5 cm cube, but it should be in dm cube. So I'm dividing that by 1000. And let's solve this. So I'm getting 0.0057 moles on my calculator. And since HCl and NaOH react in 1:1, then the moles of NaOH would be exactly the same. So I know the moles of NaOH that are being used in the reaction, which should be 0.0057 moles. So I have two things now. I have the volume of NaOH that's being used in the reaction. I have the moles of NaOH that are being used in the reaction. So we can apply the same formula, which would give us the same formula over here for moles concentration multiplied by volume. Rearranging the terms, it should give me concentration would be moles divided by volume, which in this case the moles are coming out to be 0.0057, and I'm going to divide that by 25 cm cube, but it should be in dm cube, so I'm going to divide 25 by 1000, and let's see what the answer is. So the answer that I get on my calculator is 0.228 mole per decimeter cube. So that is going to be my answer. One correction that you should make over here is, and that is that your values are accurate up to 3 significant figures. This one over here is also accurate up to 3 significant figures. So your answer is also accurate up to 3 significant figures. So this answer over here should have been written 0.0057 should have been written accurate up to 3 significant figures. So I'm going to change that, and I'm going to add a third significant figure over here. So there should be another 0 over here, 0.005070 moles. Same over here, to show that the answer is accurate up to 3 significant figures. So coming back to my point, which is that I have found the moles, or I found the concentration of NaOH. That is something that I've been able to figure out. So the concentration of NaOH is known now, and I can now go back and try and solve this question, because the concentration over here is now known. It's 0.228 mole per decimeter cube, and let's confirm that that's exactly what the concentration is. So now trying to solve this question, I would be able to find the moles of NaOH that are taking part and that are reacting with the leftover acid from the first reaction. So let's find that using N is equal to C into V. So it's going to be 0.228 mole per decimeter cube into 10.9 cm cube, the volume that was used in the reaction. The volume should be in dm cube, so divide that by 1000, and the answer that I'm going to get is, the number of moles that I'm going to get are, so these are the moles that I'm getting. It's 0.002485 moles to be exact. But since your values are accurate up to 3 significant figures, so if you're writing these moles or stating these moles in your answer, it should be rounded off to 0.0024. It should be accurate up to 3 significant figures, so round it off at the third one. So it's going to be 0.00249 moles. But use the more accurate value when you're doing your calculations. Now we found the moles of NaOH. From that, we would be able to find the moles of the leftover acid. So it's 1:1. So the moles of the leftover acid from the first reaction, they're going to be exactly the same. So the answer is going to be 0.00249 moles as well. So these are your leftover acid. But remember, if you're doing the calculation, remember the actual moles were this. Use the more exact value on your calculator. Only when you're stating the answer only when you're stating the value in your answer, that's when you're going to round it off to 3 significant figures. So this is my leftover HCl. So let's first try and find the moles of HCl that were added in excess originally. So I'm going to use the formula N is equal to C into V again. and it's going to be the concentration given is 0.2 mole per decimeter cube, accurate up to 3 significant figures, and the volume given is 100. I'm going to divide that by 1000 to convert that into decimeter cube, and this value comes out to be 0.0200, accurate up to 3 significant figures, because your values have an accuracy of 3 significant figures, so it's 0.0200 moles. So these are your moles that were initially added, and these are the moles that are left over after the first reaction. So what is the amount of HCl that actually reacted in this reaction? So these are your initial moles that you added, and these are your leftover HCl moles. So you're going to subtract the two values, the moles that were added and the moles that were left over. So it's going to be 0.2 would be subtracted by 0.00249, but remember 249 was a rounded value. Use the more accurate value, so it's 24852, and the answer would be, it's coming out to be 0.0175148 moles, the most accurate value. So these were the moles that were actually taking part in the reaction. These are the moles of HCl that are actually reacting with barium hydroxide. So let me remove all the working and let's focus on these moles now. So here are my moles, and remember to, when you're stating the value, that it should be rounded off to 3 significant figures. So this would be 0.0175 moles. This is the value that you're going to state when you're writing the answer. But remember, when you're doing your calculation, take the most accurate value forward, not the rounded value. So we can now use these moles and we can find the moles of barium hydroxide. So it's 2:1. So the moles, according to the ratio, the moles of barium hydroxide would be half of this. So I'm going to divide this by 2 to find the moles of barium hydroxide, 2:1. So moles of HCl and the moles of barium hydroxide would be half this value, and that answer would be, my calculator gives me 0.0087574 moles. And again, if you're stating the answer, it should be stated to 3 significant figure accuracy, so it's going to be 0.00876 moles if you round it off to 3 significant figures. The last part, because the question had asked us to calculate the percentage purity of the sample of barium hydroxide, the last part would be you would need to find the mass of barium hydroxide. Since you have the moles, so you can find mass by the formula. Mass is going to be moles multiplied by the MR, which in this case would be, it would be moles of 0.00. Remember to take the most accurate value forward, so it's going to be 0.0087574 multiplied by the MR, which is, so the MR according to the periodic table, barium is 137.3, oxygen 16, hydrogen is 1, and that would be, since there are 2 OH ions in the formula barium hydroxide, so this would be multiplied by 2, and this value comes out to be equal to 1.5, and then there are a lot of decimals after that. So I've written the complete value, but remember, all your values, all your concentrations of every input that you took in the question was accurate up to 3 significant figures. So your answer will not exceed 3 significant figure it cannot exceed 3 significant figure accuracy, so it's going to be rounded off to 1.50 grams. So I found the mass of barium hydroxide now, and I also have the mass of impure barium hydroxide, which is given over here, 1.6524 grams. The only thing I need to do now is to find the percentage purity of barium hydroxide. So out of 1.6524 grams, the mass of barium hydroxide comes out to be 1.50 grams. So it's 1.5 divided by 1.64 percentage purity multiplied by 100. So my percentage purity comes out to be 90.785682. Remember, even in this calculation, I'm not actually using 1.50. I'm actually using the more accurate value, which was 1.50014262. So using that value, not this value over here, the more accurate value, remember to take the more accurate value in your calculator forward. But since my value, one of the value was accurate up to 3 significant figure, my answer cannot exceed 3 significant figure accuracy, so this value needs to be rounded off. So it's going to come out to be 90 point, rounded off at the third significant figure, so it's going to be 90.8%. That would be the percentage purity of barium hydroxide in this question.